Spinning neutron stars. Let's start with the quietest sound in the universe. Here's the setup: a dead star, the collapsed core of something once 30 times heavier, packed into a sphere 12 miles across. It spins hundreds of times a second, and if it isn't perfectly smooth, it hums. Picture a mountain on its surface. Not a mountain like Everest, a mountain like a fingernail. Neutron star crust is the strongest material in the known universe, 10 billion times stronger than steel. And even that material can only hold up a bump maybe a few millimeters tall before gravity crushes it flat. A few millimeters on a star spinning 600 times a second. Here's the twist: a bump that small on a star that dense, spinning that fast, is enough to bend spacetime itself. Continuously. Forever. Not a single burst, a constant, endless, monotonous ripple pouring outward at the speed of light, tuned to one exact frequency for as long as the star keeps spinning. Physicists call this a continuous wave. It's the opposite of a crash or a collision. It's a tone, a single, impossibly quiet note held for millions of years, drowned out by everything louder happening elsewhere in the galaxy. Here's the fact that changes everything. Nobody has heard one yet. Not a single continuous wave from a spinning neutron star has ever been confirmed, despite decades of searching through data from dozens of known pulsars. The signal should be there. The theory says it must be there, and it's still too faint, buried under noise, waiting. Let that sink in. Somewhere in this galaxy, a few millimeter tall mountains, invisible, unmeasured, unnamed, are quietly reshaping the fabric of space every single second, and we still can't hear them over the noise of our own instruments. But a whisper this quiet is nothing next to what happens when two of these dead stars actually collide. Binary neutron star mergers. This is where whisper becomes scream. Here's the setup: two neutron stars, each one packing more mass than the sun, into a ball the size of a city, locked in orbit around each other. They lose energy to gravitational waves with every pass, an effect so small between ordinary objects it's unmeasurable, but between two neutron stars, it adds up. The orbit tightens, the waves get stronger, the spiral accelerates. In the final second before collision, these two objects are moving at a significant fraction of the speed of light, orbiting each other hundreds of times per second, ripping the space around them like a whirlpool. Here's the number that should stop you. On August 17th, 2017, LIGO and Virgo detected exactly this: two neutron stars merging 130 million light years away. The signal lasted about 100 seconds. 100 seconds of gravitational waves, chirping upward in pitch as the stars spiraled faster and faster, ending in a single violent burst as they collided. But here's the twist that made this event historic. Telescopes on Earth saw it too. A flash of light, a burst of gamma rays, arriving just 1.7 seconds after the gravitational wave signal ended. For the first time in human history, we watched the same cosmic event with gravity and with light. Multi-messenger astronomy, they called it. An entirely new way of doing science, born in under 2 seconds. Here's the fact that changes everything. The collision produced gold, and platinum, and uranium. Every heavy element past iron on the periodic table, the stuff of wedding rings, of reactor fuel, of every gold atom on Earth was very likely forged in exactly this kind of collision, flung into space in a radioactive afterglow called a kilonova. The ring on your finger might be older than the sun and born in a car crash between two dead stars. Not bad for 100 seconds of screaming spacetime. If two neutron stars colliding can forge gold, what happens when one of the colliding objects isn't a star at all, but a hole in space with no surface, no light, nothing? Black hole neutron star mergers. The mismatched pair. Here's the setup: a black hole several times more massive, paired with a neutron star far smaller and lighter, spiraling together the same way, energy bleeding out as gravitational waves, orbit tightening, speed climbing toward the final plunge. Here's where it gets strange. Depending on the mass difference, the neutron star doesn't always merge cleanly. Sometimes the black hole's tidal forces shred it apart before it even crosses the event horizon, spaghettifying the star into a glowing disk of debris an instant before the black hole simply swallows the rest. Other times, if the black hole is large enough, the neutron star crosses the horizon hole, vanishing without a trace, without so much as a flicker of light. Same category of event, two completely different endings depending on nothing but mass. The first confirmed detections of this exact kind of merger came in January 2020, two separate events, cataloged within 10 days of each other. After decades of searching for a category of collision astronomers were confident existed, but had never actually caught. It took less than 2 weeks to go from 0 confirmed events to 2. Here's the fact that changes everything. In at least one of those mergers, telescopes found no counterpart light at all. No flash, no glow, no afterglow. The black hole may have swallowed the neutron star so completely, so instantly, that nothing was left over to shine. Total silent annihilation witnessed only in gravity because there was nothing else left to see. An entire star erased, with the only evidence being a ripple in spacetime and nothing else. If a single black hole eating a neutron star can vanish that completely, what happens when two black holes, the most extreme objects physics allows, collide with each other? Binary black hole mergers. This is the one that started it all. Here's the setup. Two black holes, no light, no surface, nothing but pure gravity given shape, orbiting each other in absolute darkness. No matter to shred, no debris to glow, no light show of any kind, just two invisible wells in spacetime spiraling toward each other in total silence. On September 14th, 2015, LIGO detected exactly this. Two black holes, 36 and 29 times the mass of the sun, spiraling together and merging into 1.3 billion light years away. It was the first gravitational wave ever directly detected by human instruments. A century after Einstein predicted these ripples should exist, we finally heard one. Here's the number that should stop you. In that final merger, roughly 3 entire solar masses, 3 suns worth of matter, converted directly into pure gravitational wave energy in a fraction of a second. For that brief instant, the power radiated by this single collision in gravitational waves alone exceeded the combined light output of every star in the observable universe. Every star combined, outshone in a form of energy nobody could see by two invisible objects colliding in the dark. Here's the twist. Since that first detection, LIGO and Virgo have now logged hundreds of black hole mergers, and the black holes keep getting stranger. Some spin at extreme angles, misaligned with their orbit, hinting at violent formation histories. Some collide with masses in ranges astrophysicists didn't expect stellar collapse to produce at all, raising the possibility that some of these black holes formed some other way entirely, maybe even in the first fractions of a second after the Big Bang. Two invisible objects colliding in absolute silence and absolute darkness, outshining the entire visible universe in a form of light no eye can see. Let that sink in. But every merger on this list needed a beginning. Something has to trigger the black hole or neutron star in the first place. And that beginning is almost as violent as the ending. Supernova core collapse. The one gravitational wave source we still haven't cleanly caught. Here's the setup. A massive star, out of fuel, its core suddenly collapsing under its own gravity in less than a second, crushing atoms into neutrons, triggering one of the most violent explosions in the universe. If that collapse were perfectly spherical, symmetric in every direction, it would radiate no gravitational waves at all. Perfect symmetry cancels itself out. But real stars are messy. Convection, rotation, instabilities boiling through the collapsing core in the final milliseconds, all of it breaks the symmetry. And a broken symmetry collapsing at nearly the speed of light should ring out a burst of gravitational waves. Here's the twist. We've detected the light from thousands of supernovae. We've detected the neutrinos from exactly one back in 987. We have never once confirmed the gravitational wave signal from a supernova core collapse. Not a single detection anywhere, ever. Here's why this one is different from every merger before it. Mergers are clean. Physicists can predict almost exactly what the waveform should look like, decades in advance, using nothing but the mass of the objects involved. A collapsing star's interior is chaos. Turbulent, asymmetric, impossible to model precisely. nobody knows exactly what the signal should sound like, which makes it exponentially harder to pick out of the noise. The next nearby supernova, and one is overdue somewhere in our galaxy, statistically speaking, roughly one or two every century, could finally hand us that missing signal. A star dying in real time, its interior chaos broadcast directly into our detectors the instant it happens. Light arrives hours or days later. The gravitational waves would arrive first, straight from the core, before the star even finishes exploding, which raises an obvious question. How exactly do you catch a ripple in spacetime that started over a billion light years away and arrives as a distortion smaller than a proton? LIGO, Virgo, and KAGRA. The ears humanity built for a universe that has no sound. Here's the setup. Each detector is an L-shaped tunnel, arms 2.5 miles long, with a laser beam split down each arm, bounced off mirrors, and recombined. Under normal conditions, the two beams cancel out perfectly. But a passing gravitational wave stretches one arm by an infinitesimal amount while squeezing the other, and the beams no longer cancel. A flicker of light where there should be none. Here's the number that should stop you. LIGO can detect a change in arm length 10,000 times smaller than a proton. To put that in perspective, if one of those 4 kilometer arms were stretched to the distance between the Earth and the nearest star, this instrument could still detect a length change smaller than the width of a human hair. That kind of sensitivity comes at a cost. Every truck driving nearby, every earthquake on the other side of the planet, every wave crashing on a distant shore registers as noise that has to be filtered out. The mirrors hang from elaborate pendulum systems, isolated from nearly every vibration on Earth. Also, that one specific kind of vibration, one that started over a billion years ago, in a collision between two invisible objects, can finally get through. Here's the twist that makes this a global effort, not a single instrument. LIGO has two sites in Louisiana and Washington state, deliberately built thousands of miles apart. Virgo sits in Italy. KAGRA operates underground in Japan, built inside a mountain to escape surface vibration entirely. A signal has to appear in multiple detectors, separated by enormous distances, arriving at slightly different times, before anyone believes it's real. Triangulating a source means comparing arrival times measured in milliseconds across an entire planet. Humanity built a network of listening posts spanning 3 continents just to catch a shudder a billion times smaller than an atom. And it worked. But every merger LIGO has ever caught is a single discrete event, a specific chirp, a specific moment, a specific source. What if most of the universe's gravitational waves aren't discrete events at all? The stochastic gravitational wave background, the hum underneath everything. Here's the reframe. Every merger too far away, too faint, or too overlapping with another to be individually identified doesn't just disappear. It adds up. Millions of black hole and neutron star mergers happening across the observable universe at every moment layer into a continuous directionless hiss of gravitational waves, background noise permanently running underneath every clean signal LIGO ever detects. Here's the twist. This background isn't a problem to filter out. It's a measurement in its own right. In 2023, pulsar timing arrays, international collaborations tracking the arrival times of radio pulses from dozens of pulsars scattered across the galaxy, announced evidence for exactly this kind of background, but at a much lower frequency than LIGO detects. Pulsars act as a galaxy-sized detector, with each pulsar behaving like one arm of an impossibly large gravitational wave observatory, its timing subtly disturbed as waves with wavelengths of entire light years pass through the galaxy. Here's the fact that changes everything. The source of that particular hum is likely supermassive black holes, millions to billions of times the mass of the sun, merging at the centers of colliding galaxies, too numerous and too overlapping to ever pick apart into individual events. Not one collision, not 1,000. An uncountable, continuous chorus of black hole mergers stretching across the entire history of galaxy formation, blended into a single indistinct roar. Every clean chirp LIGO has ever detected is a single voice picked out of a much larger unresolvable choir that never stops singing. If ordinary matter colliding can produce a background hum like that, What could produce a gravitational wave signature from something that isn't matter at all? Cosmic strings, hypothetical, possibly non existent, possibly stretched across the entire observable universe. Here's the pitch. In the earliest fractions of a second after the Big Bang, some theories predict the universe underwent phase transitions, the same kind of process that turns water into ice, and some of those transitions could have left behind defects, not cracks in ice, cracks in spacetime itself. Infinitely thin, unimaginably dense filaments, potentially stretching across the observable universe, under tension so extreme that a single inch of cosmic string could weigh more than the entire Earth. Here's where it gets strange. If a cosmic string forms a loop and that loop oscillates, it can develop what's called a cusp, a point that briefly moves at very close to the speed of light. That cusp would fling out a sharp, distinctive burst of gravitational waves, unlike anything a merger produces. No chirp, no ring down. A completely different waveform entirely. Nobody has ever confirmed a single cosmic string exists. Not one. They remain purely theoretical, a prediction from certain models of particle physics in the early universe, never observed directly, never ruled out entirely either. Here's the fact that changes everything. Gravitational wave detectors are one of the only tools that could ever prove they're real. Cosmic strings wouldn't shine. They wouldn't block starlight in any obvious way. They are, in every practical sense, invisible to light. But a burst from an oscillating loop would leave a gravitational wave signature unlike any known astrophysical source. A fingerprint from an object made of nothing but geometry, tension, and the leftover scar tissue of the Big Bang itself. We may already be listening for the sound of the early universe tearing, which brings us to the strangest gravitational wave source of all, one that isn't a collision, a hum, or even a leftover scar, one that comes from the birth of space and time themselves. Primordial gravitational waves, from inflation, from before there were stars, before there was light, before there was matter to collide at all. Here's the pitch. In the first tiny fraction of a second after the Big Bang, the universe may have undergone an unimaginably fast expansion called inflation, stretching space by a factor of trillions in less time than it takes light to cross a proton. During that expansion, quantum fluctuations, the tiniest random jitters allowed by physics, would have been stretched instantly into full-sized ripples in spacetime itself. Here's the number that should stop you. These would be the oldest gravitational waves possible, generated not by any object, but by the fabric of the universe expanding faster than anything before or since. If they exist, they've been traveling essentially unchanged for over 13 billion years, since roughly 1 trillionth of a trillionth of a second after the beginning. Nobody has detected them. Not with LIGO. Not with pulsar timing. The signal, if it's there, is expected to be encoded not as a chirp or a hum, but as a specific twisting pattern of polarization in the cosmic microwave background, the oldest light in the universe, called B-mode polarization. In 2014, one team announced they'd found exactly that pattern. Within months, follow-up analysis showed the signal was almost entirely galactic dust. Another announcement, undone by ordinary particles in our own galaxy, getting in the way of a signal from the dawn of time. Here's the fact that changes everything. If primordial gravitational waves are ever confirmed, they wouldn't just be the oldest gravitational waves in existence. They'd be direct physical evidence of inflation itself, a theory currently supported by strong indirect evidence, but never confirmed with a single direct detection. Proving they exist would mean detecting a ripple generated before atoms, before light could travel freely, before the universe was even a billionth of a second old. Let that sink in. Every gravitational wave on this list, from the quietest pulsar hum to the loudest black hole merger, is a message about something that happened. This one would be a message from the moment space itself began expanding. So here's where the science actually stands. Spinning neutron stars hum too quietly to hear. Merging neutron stars forge gold. Black holes swallow neutron stars whole, sometimes without a trace of light. Two invisible black holes colliding can outshine every star in the universe combined. Supernovae should ring out in gravity, and haven't yet. A planet spanning network of lasers listens for a shudder smaller than a proton. An uncountable chorus of ancient mergers hums beneath every signal we've ever caught. Cosmic strings, if they're real, would sound like nothing we've heard before. And somewhere in the oldest light in the sky might be the echo of the universe's very first instant, still waiting to be confirmed. Every single one of these is spacetime itself, physically ringing like a bell, and until 2015, humanity had never heard a single note of it. Not bad for stick figures on a rock.